Okay, what we're going to talk about tonight is composite functions. And the reason we're going to talk about composite functions first, and I think I talked to you a little bit about them last time, about composite functions and showed you some examples. There are problems that it would be exceedingly difficult to do if all we had was the product rule, the quotient rule, and the power rule. And this, for example, would be one of those problems. You wouldn't want to try to take the derivative of this by actually multiplying out x cubed plus the square root of x times itself 4 times. Because, well, if I were to have to do it, I could do it. I don't want to, but I could do it. I know how to do it. But I'd have to start over here on this board and work my way down that board and then go to the top and down the board again and then go to the board behind the screen and probably start back over here before I ever got finished. I would have a whole page of paper taken up just trying to get it into something I could do the power rule with, or I would have to do the product rule, but I would have to do the product rule by doing the product of the first one times the product of the next one and get that derivative and then take that times the product of the next one. And it would be so many steps it would be insane. And I would get very tired of it and probably make a mistake and get the wrong answer. So what I want to do, the idea that I want to get across to you this first part is the idea of what is an inside function versus an outside function. And hopefully this is a visual enough idea that you won't have any trouble figuring out what I mean by that. In this function, f of x, f is actually made up of 2 pieces of 2 different functions. F's outside function, F's main job, is to take whatever is inside these parentheses and raise it to the 4th power. So that's what f does, is it takes whatever's in the parentheses and raises it to the 4th power. What it does that to is what's inside the parentheses. So in this case, the inside function is that x cubed plus the square root of x that's inside those parentheses. And as long as you'll be able to recognize the inside and the outside functions of what's called a composite function, then we don't have to go through a lot of practice about, okay, let's figure out what f of g of x is and what's g of f of x and all that, because that's not really the point. What I want you to be able to do is to figure out which one of the functions is the one that's on the inside. And that's not as hard to tell as what you might think it is. So what we're going to do is we're going to practice with that a little bit. So here is a composite function. What would you think the inside function is for this function? Yeah, it'd be 2x cubed minus 6x because it's inside the radical. Okay? It's inside the radical. So the inside function is this. And then, of course, the outside function is the radical. Now, in order to take a derivative of that, just tell you right up front, in order to do a derivative of that, what we would have to do is we would have to change the outside function to a 1/2 power. Because we don't have any rules for radicals. But if we change the radicals to powers, then we have all kinds of rules we can use. So we would actually change that to the same inside function, that 2x cubed minus 6x, but we would change it to a power. Okay? So the outside function would be the radical or the square root function or the 1/2 power, but the inside is the expression that goes underneath that radical. This one is an example of something that's more than just a composite function, although there is a composite function in there. This function actually consists of a product, because this is factor 1, and this is factor 2. So it's a product of those two factors, but in order to take the derivative of our second factor, we would have to have what we're going to call the chain rule. We would have to recognize that the outside function for that second factor is the fourth power, and that the inside of that chain rule function is going to be the x cubed plus the square root of x. So all the tricks that we've learned before, we're still going to need. We're still going to recognize that if we have a denominator and the variables in the denominator, we need to move that variable up to the numerator by changing the sign on the power. If we have a radical, a square root or a cube root, we're going to need to change that radical into a variable with a power on it. We still need to know how to do those things. The only thing new is realizing that this particular kind of derivative is going to be a two-step process. And we have to figure out what the two steps are. So I'm going to go back, and I'm going to actually skip a bunch of these that are in your notes. You can just mark right through these if you want to, because this I have found does not help you figure out what we're going to do in the calculus. So I went ahead and printed them out, but in the interest of time, knowing that we're going to get tired a long time before we get finished with these, then we're going to skip all of these and go to the parts that have to have calculus. Now, I do have, if you want to go back and fill those in, I do have a recording already made where I'll work those. But I want to start here. I want to start with this example. And you're going to see some of the ones that we looked at here, because we're going to actually take some of these derivatives. So suppose we have this function. And somebody's been nice to us already. They didn't leave it as a radical. They took it out from under the radical and they wrote it with power. Okay? Our outside function is the parentheses to the 1/2 power. Okay? Our inside function is what's inside the parentheses. This is the way the chain rule works. I'm going to tell it to you in words. I'm not going to show it to you like a formula. I'm going to tell it to you in words. We're going to take the derivative of the outside and multiply it times the derivative of the inside. So the outside function is something raised to the 1/2 power. And the way that I do the derivative of something raised to the 1/2 power is I take the power down in front, and then I subtract 1 from the power. Now, I know I didn't put the inside, I didn't put the guts back in yet, but they're still in there, okay? Those don't change. It stays what the original was. So you don't do anything with that at that point. You just bring it along. And then at this point now, we do the second part. The derivative of the inside function is 2 times 3 is 6x, and 2 minus 1 is 1, so that's 6x to the first, minus 5, because that's x to the first. 1 times 5 is still 5. But when I say x to the first minus 1, that becomes x to the 0, and x to the 0 becomes just 1. Okay? And then it says take the product. Okay, fine. I'll multiply by that. Now, at this point, what you have is dy dx. It is that product. I didn't clean it up or anything yet. I didn't, go ahead and do the little things like say 1/2 minus 1 is negative 1/2, but that's what it is. Okay? So all I would do at this point is I would say 1/2 times 3x squared minus 5x to the negative 1/2 power times 6x minus 5, and I would call it a day, because at that point I've done the calculus. At that point I'm finished. Unfortunately, the people that program for my stat lab and my math lab apparently like torture. They like algebra a whole lot more than a math teacher does. They would go ahead and they would start simplifying that, and they'd wind up with something that doesn't look much like that. But if you'll type that in exactly the same way that we just wrote it, that's the right answer, and the program will accept it. We can put it in there, okay? If you ever type in an answer in my math lab and it says, no, that's wrong, and then you go through and you look at all these steps, but the first step that they typed in pretty much looks like what you typed in, there's that little button up there that says Ask my Instructor. Click that button and say, would you please look, because I think the answer is this, and it says the answer is this, and I want to know if I did, where did I go wrong or did I go wrong? Okay? Most of the time I'm going to say, well, okay, you missed a sign maybe here somewhere, or maybe you left something out, but no, you did do it right, and I'll give you credit. So you don't need to do all that algebraic simplification. Yes? This is called the chain rule. And it's called the chain rule because you have the first link is the outside, and then the other chain actually connects together inside the first one. And they're linked together when you do the derivative. That's why it's called the chain rule. Okay? So it's CHAIN, the chain rule. So what I'm trying to tell you is that my math lab would rewrite this. Let's see, they wouldn't even do that. They would rewrite this like this. They would rewrite it and make it look like that. I don't think that looks a bit better than the other thing did. And in fact, if I was going to plug in x equals 5, I don't know that I would care which way I plugged it in. I could probably plug it in just as well on the first form of it as I could the second form. Although if I'm going to plug in x equals 5, I'm going to use nderiv to start with. And let the calculator do the arithmetic. So this is the acceptable answer. There will be a few times, I will warn you, there will be a few times where we will minimally combine and clean up a chain rule derivative because we're going to have to use it for another step. And it'll be easier to use if we kind of shrink it down a little bit, but that's the only reason for doing it. This is saying the same thing. Take the derivative of that function that's been raised to a power. So it's very, very similar to the one that we just did. We have an outside function, something raised to the 8th power. We have an inside function, the stuff that's inside the parentheses. what we're going to do is take the derivative of the outside first. Bring the 8 down in front and reduce the power by 1 and call it 7. Then we're going to take the derivative of the inside function, which was x squared plus 5x, and the derivative of x squared plus 5x is 2x plus 5. And we're done. There is no need to do anything else to that. I kept telling you it was going to get easy. Just click on the first problem that you missed so that I'll be reminded to go in and look at yours, and I'll go in and review your homework, because sometimes it's simply that you didn't put a set parenthesis where it wanted it or something, and that's why I say sometimes you do have, sometimes it actually is easier to clean it up a little bit just because it's not as many parentheses to type in. Like, for example, here, I might go ahead and multiply 8 times that 2x plus 5. So that all I have is 2 sets of parentheses, and then I'm less likely maybe to misplace something. But I will look at those for you, and that's one of the reasons too that I don't give you as many of my math lab problems as what I used to, and I don't count the grades as heavily because I know that it's frustrating and aggravating. You just grit your teeth every time you do it. But in order to be able to get booked the price we do, we've got my math lab, and rather than sit and do page after page after page of homework and not know if you're doing it right, and because the guys give you the ones in the back of the book, well, they simplify them out too. So that's why I look at the Shobi homework more than anything else. The Shobi homework counts more because when I'm grading Shobi, if I gave you that problem to do, I would look to see if you got that step. If you got that step, I'm done. Everything you wrote after that is fine, but I'm not looking at it. I want to see that step. Okay? Now, the only thing I will caution you about here, these are 2 things that are really common errors. Most common error is to forget to multiply by the derivative of the inside. Everybody remembers how to do the outside part, but they forget you have to also multiply by the derivative of the inside. That's that 2-step process. And when you write your answer needs to look like this, not like this, because it's not the derivative of g of x. That's not the same thing. The notation is still f prime of whatever g of x was. And most of the time, I'm not going to write it as f prime of g of x anyway. I'm going to say f of x is equal to this, and then let you figure out what the derivative is without throwing in all the extra f's of g's of h's and all that stuff. I'm going to try to keep it simple. I think she's allergic to me.
She's been allergic to math.
Okay, now this one is a little bit more complicated. Okay, just a tad more complicated. Because when you look at that, do you see the chain rule? Do you see where the chain rule is going to have to be used? Yeah. But is that the only rule we have to use? No, we also have to use what else? A product rule, because that's the product of 4x times the quantity 3x plus 5 that's been raised to the 5th power. So it's a product rule first and foremost, and you'll have to learn to recognize that. This is factor 1. This is factor 2. No, factor 1 being the first part of the multiplication. Okay, when we So remember that the way that we do a product rule is we take the first factor and we multiply it by the derivative of the second factor. And then we add it to the second factor, multiply by the derivative of the first factor. So this is factor 2 and this is factor 1. Basically, we take derivatives of both factors and then we swap their derivatives between them and add them together. So I'm going to go slow and step by step to make sure that you can follow me. The first thing I'm going to do is I'm going to take factor 1 and I'm going to take its derivative. And that derivative is just 4. Then I'm going to take factor 2. And factor 2 is where I'm going to need the chain rule when it's time to take the derivative. So there's my second factor. And factor 2's derivative, which I'm just calling F2 prime, they like using these in the book, but I think it's easier if we can simplify that down to single letters. I'm going to use my power rule and bring the 5 down in front of the parentheses. Then I'm going to reduce my power by 1. But then I'm recognizing that I had something that was the inside function, and I need to take its derivative as well. So the derivative of 3x plus 5 is 3. Now before I do anything else with that, does anybody have any questions about where anything came from? No, that actually is part of tonight's class. The 3 is part of the chain rule. Okay, that's the new stuff.
3 is the one that's got the function next to it, right? That's how you put up the derivative. Does that make sense?
I'm not sure I understand what you're saying.
It's the only one that's got a letter next to it, so that's why.
Yes, the derivative of the plus 5 would have been 0.
Okay.
So I didn't write down the 0 because we don't need to. Okay? So yes, the derivative of 3x plus 5 is actually 3 plus 0. And we just wrote that as 3. Okay? Anything else that you don't understand where it came from? Okay, now since we're going to do some swapping around, we may decide to combine some things. This is as simple as it gets. There's not much I could do to simplify any of that. But I do look here and I say, well, you know, I've got a 5 there and I've got a 3 there. And I know that 5 times 3 is 15, so rather than write down 5 times 3 times something, maybe it would be simpler and less trouble if I just say that's 15 times that set of parentheses. That'll be a little less work when I start swapping the derivatives around. Now it's time for them to trade derivatives. So now I'm doing product rule. I'm finished with chain rule. I use chain rule right there. I'm finished with it. Now I'm ready to go to the product rule. Product rule says take factor 1 and multiply factor 1 by the derivative of factor 2. And then it says, take factor 2, and that's the original factor 2, not its derivative, and multiply it times the derivative of factor 1. And then add those together. So there's the derivative of this original function that they gave us. We just had to pick it apart to be able to do that. And you're going to hear me say this a lot. Calculus does not give pretty answers. Calculus gives ugly answers. Very ugly answers. But it's okay if they're ugly. We learn to like ugly. Because ugly is better than trying to tie the bow around it, which is what takes all that algebra stuff, okay? Now, if you want to make it a little less ugly, that's okay. But about as little less ugly as I'd want to make it is I might do this much. 15 times 4 is 60x. And I might bring that 4 out in front instead of having it hanging out there at the end. Just because I'd be more afraid I'd forget about it being there if I didn't stick it in the front. But other than that, I wouldn't do anything else. And I can tell you for a fact that if you do that in my math lab, it goes to about 3 more steps to get a result that doesn't look one darn bit better. In fact, to me, looks worse than what the original problem did. Because what they do is they factor out 3x plus 5 to the 4th power as the greatest common factor. And I don't see how that improves anything. I really don't. That's just unnecessary. Okay? I will leave that up because this is not a short process. I'm going to do this lesson first, but then the last 2 lessons are going to go together because they're going to go quick. Even though everybody in here is saying, oh, God, she's talking about exponential and log functions. I hate those. That's how to do derivatives of exponential and log functions. And you don't need to know 2/3 of what was in Chapter 10 to be able to take derivatives of exponential and log functions. It's really a very easy process. It's as easy as the power rule was. It really is. So we're okay now? Anybody have any questions? And Chris, don't forget, I'm recording this, so you're going to have availability to back it up, slow it down, fill in your notes. I know it's always kind of hard when you come in after you've missed a class. Okay. Yes, there is a chain rule problem here, but before you worry about where the chain rule problem is, what kind of a problem is this? It's a quotient rule. It's a quotient rule. That means it's got a numerator and it's got a denominator. This is its numerator. This is its denominator. And what the quotient rule says is that you begin with the denominator. You always begin with the denominator. And you square the denominator. And then you start off in the numerator with the denominator. So you begin at the bottom. And you multiply the denominator times the derivative of the numerator. And then you're going to subtract from that the numerator times the derivative of the denominator. It's a lot like the product rule. The big difference between this and the product rule is product rule you wind up with the sum of two things. You wind up adding. With the quotient rule, you wind up with another quotient. So that's why you start on the bottom and you keep the denominator you had, but you square it. And then when you get to the top, because it's a subtraction problem, it's important to remember that you're doing the denominator times the numerator's derivative first. That's why I say start with the denominator and do everything with the denominator first and end up with the part where the numerator comes first. So, always go through that process and keep you from making a mistake. Because the biggest mistake here that anybody ever makes is that they will swap those two around. And you have to remember that 7 minus 3, for example, is not the same as 3 minus 7. You'll come up with a problem with something being the opposite of what it's supposed to be. Okay, so be sure that you always lead off with the denominator. So this is where we're going. Now we're ready to take our derivatives. We've got n, we know what n is. We've got d, we know what d is. So I can fill that much in. And I know I'm going to subtract. So my denominator, d, is x minus 1. And this says I'm going to square it. So I do. And then it says I take that same denominator and I lead off with it in the numerator. So I put it up there. But now I've hit a snag because I need to know what the derivative of the numerator is. So over here on the side, I need to find n prime. What kind of an expression is the numerator? What kind of a rule do we need to take the derivative of that numerator? You need your chain rule. Because it's got an outside set of parentheses with some algebra stuff inside of it. So we're going to take that power of 7 and bring it down in front of the parentheses. Then we're going to subtract 1 from that power and make it a 6. And then we're going to keep what was inside the parentheses. But we're also going to take the derivative of what was inside the parentheses, which is 3. And then since we're going to have to multiply this times this, we're going to try to shrink it up as much as we can before we use it. So 3 times 7 is 21 times the quantity 3x plus 2 raised to the 6th power, and now I'm ready to use it. And I've got my subtraction in there a little bit too early, so I'll move it down here out of the way. So I've done this part. And now I'm ready for the last step. And the last step says take the numerator, that's this, take it exactly as it is, don't change it, don't do anything to it, and multiply it by the derivative of the denominator. And that's 1 times x to the 1 minus 1, which turns out to be 1 minus 0, which I don't need the minus 0, so it's just 1. At this point, I've got y prime, or d sub x, whichever way you want to call it. They're all just symbols for the derivative. So I've got my symbol for my derivative. That's all I need.
Can you explain to me how you got the 1 again? At the end?
From x minus 1,
Yes.
what's the derivative of x?
Okay.
Yeah, just 1. Just 1, and then the derivative of minus 1 is minus 0. 1 minus 0 is 1. It's the little things that I always like, where'd that come from? Okay? Now, could you do anything else with it? Yes, of course. Who wants to? You could, but who wants to? One thing you cannot do, and I'm going to warn you of this right now, don't you dare try to cancel that and that, because you can't do that. The reason you can is because you can't cancel it out of this. If you can't take it into both of them, you can't take it out of either one of them. Okay? Truthfully, when you get ready to put it in my math lab, I'd probably ditch the 1. You don't need it. It's not doing anything. And if you wanted to, you could go ahead and say that's 21x minus 21, but you don't have to. It works without doing that. So that's as much simplification as I'm going to do. I'm going to stop with the first step because I'm teaching you calculus. I'm not worried about making you feel inferior about doing algebra. Because most people do get very frustrated trying to push those letters around and make sense out of them. Okay? Anybody need this up here a little bit longer? Are we ready? Anybody have questions? Potentially you could, yes.
Are we going to see how to work on those?
Yeah.
Or
I would never give you something to do that I hadn't showed you how to do. Okay? We have an application problem. This application problem, the actual calculus that we're going to have to do is very simple. It really isn't difficult at all. The difficult part of this problem is figuring out what it is we're supposed to do with it because of the way that it's worded. And I'm accustomed to people having lots of questions, and the first one they usually have is, what do they mean 30 work hours in a day? There's not 30 hours in a day. How can you have 30 work hours in a day? So we're going to have to explain that. Okay? So we're going to go through this first and talk about what this problem means. First of all, this is a revenue equation. We're talking about money. This is the revenue equation for a city, and it's the revenue from where they've collected fines from parking tickets. It's a source of income for the city to maintain their parking lots. Their revenue function, which is 8,000 N over N plus 2, is based on N, and N is the number of work hours every day that are spent collectively by more than one person writing parking tickets. So when you look at that 30 work hours a day, don't think there's only 24 hours in a day. They can't do that. Yes, they can. If they've got 2 officers that work 15 hours a day, then that's 30 work hours. If they've got 6 officers that spend 5 hours a day writing tickets, then that's 30 work hours. That's the total number of hours that the total number of officers together worked. Okay? So we're talking about multiple police hours collectively. So N represents the number of work hours. Be sure you understand that that's what those are. Okay? So on a typical day, they come in, they get their little parking trolley things and ride around, or they ride a bicycle or whatever they're going to do to go around, and they're going to get parking tickets. And what happens here is that it's just like it is for us, it's flu season. There's a flu epidemic. And, of course, they get sick just like all the rest of us do. So maybe an officer calls in sick, says, I can't come in today. They don't have anybody else to replace that officer. It's more important to send the officers out on other more important things than writing parking tickets. So what happens is they have fewer hours to be able to spend, fewer labor hours to be able to spend on writing parking tickets, which means that then they're going to be making less money because they didn't write as many parking tickets. Okay? So what happens is on the first day of the epidemic, the first day at the start when they first start out, they're using 30 work hours daily. That's before anybody got sick. So that's where they start. Before anybody got sick, they're getting 30 work hours a day in writing those parking tickets. But as soon as the flu epidemic starts, that number is going to start decreasing. It's going to start decreasing at the rate of 6 work hours a day. Now, notice that this is 6 work hours per day. That itself is a rate of change. Okay? That's a rate of change. And this expression isn't in work hours alone, it's work hours per day. That's how we know it's a rate of change. So we're just going to tuck that away and remember it. So what we really need to do then to solve this problem is we need to figure out, since it's asking us how fast is revenue from parking fines decreasing when that epidemic starts out. How fast is the revenue going to decrease? Okay? You know it's decreasing because it's going down 6 work hours a day. That 6 hours translates to money. Okay? So what that means, since this is the revenue function, is what we need to do is we need to find the derivative of the revenue function. We need to find R prime. I have no clue why that thing is doing that. Let's see if that stops it. Hopefully it will. So we need to find R prime of n. What kind of a rule does R prime make us have to use to begin with? Quotient rule, because it is a quotient. Okay, that means we need to take the derivative of the numerator and the denominator. So we'll do that first. The numerator is equal to 8,000 times n, and its derivative is just simply 8,000. The denominator of the function is n plus 2. And the derivative of that denominator is just 1. Because that's 1 times n to the first power, so its derivative is 1, and the derivative of the plus 2 is 0, so we don't bother to write that down. And then because it's a quotient, we're going to start off with the denominator. And we're going to square it. Then we're going to move to the numerator. and we're going to keep going with the denominator, so we're going to write n plus 2 again. And then we're going to take the derivative of n, the numerator, and multiply times that. And then to that, we're going to subtract the numerator, the original numerator, which is 8,000n. And we're going to multiply that by 1, not that that's real hard to do because it's not going to change anything. Now this would be a tad easier to use if I didn't have all those parentheses in there. Since I'm going to have to do a little more work with it, I think I might want to try to clean this up a little bit. So I'm going to try to rewrite r prime of n with a few less parentheses. So 8,000 times n plus 2 is 8,000 n plus 2 times 8,000 is 16,000 minus 8,000 n. And that's all going to be over n plus 2 squared. And happily enough, the 8,000 n's cancel in the numerator. So my derivative actually looks like this. Now, is everybody good up to that point? Okay. It says they want to know how fast the revenue from the fines is decreasing at the outbreak of the epidemic. And it told us that the value of n at the outbreak was 30. So we need r prime of 30. And that's 16,000 divided by 30 plus 2 is 32 squared. At this point, I'm ready for a calculator. Mm-mm. 30 plus 2. You're wanting to square the okay? So I'm going to divide that by 32 squared. And that comes out to be 15.625. Okay? And then since it's decreasing, let me get the calculator out of the way. Since it's decreasing at that point by 6 hours per additional day, then we're going to multiply that times 6, or times negative 6. Because this is the change in the revenue. But this is the change in the number of work hours. See, this was based on the work hours, but it's the revenue as a function of work hours. And this is how the work hours are actually decreasing. So what we're going to do is we're going to take that 15.625 and we're going to multiply it times negative 6. and we get negative 93.75. So now we need to make sense of this and be able to answer the question. How fast is the revenue from parking fines decreasing when the outbreak starts? How fast is the revenue decreasing? Not how fast is the work hour decreasing. How fast is the revenue decreasing? Because that causes a decrease. The work hour decrease causes a decrease in the revenue. It's a lot more straightforward than what it appeared to be. Because when you first read the problem, it all sounds very complicated. But when you realize that it's only asking you to find the rate of change of the revenue, and then it gives you the rate of change of the work hours, then it's a pretty straightforward process. So the revenue from parking fines is decreasing by $93.75 per day after the beginning of the epidemic. That's the answer to the question. Now that doesn't sound like so much. You think, well, that's, like $100 a day. Yes, that's $100 a day every day for however long it takes everybody to get back to work from the flu epidemic. And that might be a month. So that might be 30 days, and it's decreasing by $100 for each additional day. That could be quite a bit of revenue that the city's going to be missing. So while the revenue might, or while the city fathers, the city managers might be, they might be a little bit sad about the cops being sick, they're more sad about not making all that money. Okay? That's actually the last of our chain rule problems, except for one that you're very familiar with. You did compound interest in Math 1630. All this is going to do is show you that calculus supports what you would learn from doing compound interest problems. So we're going to couch the problem in a little bit different way from what we're used to seeing. Start out by saying we're going to deposit $500 in an account that has an interest rate of R%. Now I want you to pay careful attention to the fact that this says R%, because that's going to make a difference in the way this formula looks, because you're going to say, wait, our formula didn't look like that. So it's an interest rate of R% per year compounded monthly. And at the end of 10 years, the balance in the account, and I'll show you the graph in Figure 11 in a second, the balance in the account is given by this formula for future value. You started out with $500. You're compounding it monthly for 10 years. So that's 120, 12 months a year times 10 years. And since this is R%, we're just going to list that as R, but remember, normally when we plug into that formula, we had to change R to a decimal. Like if it was 12%, we had to change that to 0.12. Okay, well in this case, since we're using it as a percentage, we can't just put 12 in the denominator where the formula usually just says How many times a year do you compound? We've got to take into account the fact that we did not change that to a decimal. So that's why that says 1,200. It's because we're not changing R to a decimal. Our R is actually being plugged in as a percentage, straight percent. What we want to find is we want to find the rate of change in the future value with respect to the interest rate. In other words, how much faster is our money going to grow for different interest rates, one to another? Okay? What is the influence of the interest rate on how fast our money is going to grow? What does the word rate of change tell you that you're going to take? A derivative. Okay? You're going to take a derivative. What do I need to think about doing to take that derivative? Is it a product rule? Think carefully. Is it a product rule? Remember, product rule is a factor with the variable times another factor with the variable. Do we have the variable showing up in two different factors here? No. It's tempting to think it is because you see multiplication with those parentheses, but it's not. It's just simply a constant. That 500 is just a constant. That's all it is a coefficient. That 120 is a power. We can deal with a power even though it's a big power. We can deal with the power. So what's the calculus rule that we need to use to find this derivative? That's right. We need to pull the power down in front, drop it by 1. But because we have a function inside that power, we have to do a chain rule. Okay? So we're going to find A prime. So we're going to bring 120 down front. We're going to keep the 500 right where it is. We're going to keep what's in the parentheses just exactly like it is. We're going to drop the power by 1. Then we're going to take the derivative of what's inside the parentheses. And before I have you take that derivative, I'm going to rewrite the inside part of that to make it a little easier for you to see what the derivative is. So this expression is exactly the same as if I write 1 plus 1 over 1,200 times R. That way you realize 1 over 1,200 is just a number. It's just another number. Okay? So the derivative of 1 plus 1 over 1,200 times R, what's the derivative of 1? 0. Plus, what's the derivative of a number in front of R when R is just being raised to the first power? It's just a number. Because when I pull that 1 down in front, that's 1 times 1,200. 1 times 1 over 1,200. And then what happens to R? It goes away. Because when I take its exponent and reduce it by 1, it has no exponent anymore. It's a 0. So it becomes 1. So the derivative of what was inside those parentheses is just 1 over 1,200. Okay? I want to make sure you understand where all that comes from, because the rest of this is actually a very, very simple thing to plug into. You just got to do a little arithmetic, and the calculator's got to handle all your arithmetic for us. You see where everything came from. The 120 down front was the power that was on the parentheses. The 500 was already there, so we just left it there. We took one away from the power on the parentheses and kept what was in them. Then we took the derivative of what was inside the parentheses, tacked it onto the end. That was the chain rule part. Now, all the arithmetic, all the work we're going to have to do at this point, since there's nothing right now we can do about that, because we have to put what's inside the parentheses together and then raise it to the power. But what we can put together, what we can collect up, is we can take 1 over 1,200 times 120 times 500 and come up with one single number instead of having to have three. Oh, that's supposed to be 500. And I would have been wondering about that, too.
I was wondering about
Okay. Thank you for catching that. Okay, so 120 times the 500 times the 1 over 1,200. And when I multiply that all out, that's just 50. So there's your derivative, and it doesn't look nearly as ugly as what you thought it was going to, or at least not as ugly as what I thought it might look like. It actually turns out to look pretty simple. And then it says, find the rate of change if R is equal to 5. Okay, that means I'm finding A prime of 5. Pull the calculator over here out of the way so we can evaluate that. And I'm going to start out with what's inside the parentheses. 1 plus, and since it's going to do the division before it does the addition, I'm not going to put the parentheses. 5 divided by 1,200. Is 1.004, yada, 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 but I need to now raise that to the 119th power. And I get 1.60, so forth. And now I need to multiply that answer times 50. And that comes out to be about $82 and a penny. And I'm going to say that's just approximately $82, and that's $82 per percentage point increase at 5%. So my conclusion here for that particular problem is when R is 5%, the future value of the investment is increasing by about $82 per point increase.
The same could be said,
Or per additional point. Okay?
so all you would have to do for the,
7 plus 70.5.
That's exactly what we're going to do. And in fact, I'm going to be kind of lazy about it. I'm not even going to rewrite the sentence. I'm going to pull the calculator back up, get it over here out of the way of that again, and since all I need to do is do the same thing I just did, but I need to use 7, then I'm going to say 1 plus 7 divided by the 1,200. Raise that to the 119th power, and then multiply that times 50. And you see that at 7%, when the initial interest rate is 7%, then the future value of the investment is increasing by about $99.90. Or you could even say by about $100, because this is not precise. The derivative is more like an estimate at a single point in time, because it's kind of hard to pinpoint down to, okay, was that at minute 2 or was that at minute 2 and 35 seconds? So it's, it's actually changing a little bit on either side of that. And that answer should be logical to you, because what do you expect to happen to the future value of your investment if you get a higher and higher interest rate? What's going to happen to the actual way that your investment grows? It's going to grow faster, okay?
Now, is this per month or is this per year?
That's percentage point, per percentage point. That's the overall investment change. Okay, that's the change in the investment.
Okay.
Not per day, not per month, because that's not the variable we're looking at. We're looking at per percentage point change. Okay, interest rate change. Everything else has remained the same, because basically we're talking about how much has it changed at the end of 10 years. Okay, this is a 10-year investment. Okay.
So in 10 years, it's going to increase 7%, $99.90.
Yeah.
this is where I bet, something like that, like, when I look at that, I just don't see the answer, like, the per point view. I don't know why.
Okay. Look at the problem. Let me help you think through this. What is the independent variable in the formula? Is it time? Okay. Is it in the amount of money we initially invested? Is it in the compounding period? What's the only variable in the problem? The percentage point. So since that's the independent variable, just like when you're talking about speed, is miles per hour or feet per second? The independent variable there is going to be the distance that you travel and however that's measured. And your independent variable here is your percentage point. And here it's being measured in whole percentage point. Okay? So that's why we have to word the question, but the answer at the end, that it's the change in the value of the investment per change in the value of the percentage point that we're changing. Because think about this, if you're going to make an investment, are you going to get the same rate of return regardless of what bank you go to or what money house you go to? I've seen several advertisements the last couple of days on different bank signs. They have a 3-year CD, and they're all excited because their 3-year CD is now up to a whole big whopping 1.325% interest rate. But then there's still another bank that only has 1% for that same CD, and there's another one that has 1.347%. Now, what those represent. And the big thing to remember when you're answering these is if it's an average rate of change, that's from point A to point B. So the rate of change is still so much per whatever that input variable was, but it says from point A to point B, this changed by this much per whatever that unit was. It changed, okay? It increased by, it decreased by, past tense. But if you're talking about a particular derivative at one single point in time, then the language is always it is increasing by, or it is decreasing by. Or even in the case of the one on the test where was the Alzheimer's patients over the period of years, since some of those were in the future, it's perfectly okay to say in 2030 the rate is expected to be increasing by. Because, you know, we can't say, well, it is increasing in 2030. 2030 is not here yet. Although I didn't count on for anybody saying that because you're still learning how to write those. Okay? But it's always the present tense when you're talking about derivatives, and it's always past tense when you talk about average rate of change. Okay, this is actually the last of the chain rule problems. And we did pretty good because we're ready for about a 10 or 15 minute break. And then we're going to come back and we're going to do derivatives of exponential and log functions. And there's not very many examples to go through on either one. So take a break. We'll come back and do that.